So in this session, I'd like to show you how to solve the Lane-Emden equations analytically. Just single case I'd like to show you. At first, I'd like to review the Lane-Emden equations. Lane-Emden equations is expressed 1 over g squares d g squares d theta d g equal minus theta to the n equal. We just only consider very simple case. As n equals 0. Equations becomes 1 over g squares d g squares d theta d g equal minus 1. So from this equation, this is gonna be expressed dg squares d theta d g equal minus g squares. You could perform the integrals for g squares d theta d g equal minus 1 over 3 g squares plus integration constant. So this is the integration constant. Then by dividing by the theta squares, so d theta d g equal minus 1 over 3 g plus c sub 1 over g squares. One more integrals you could perform. It becomes theta equal minus 1 over 6 g squares minus c sub 1 over g plus c sub 2. Another integration constant. Then once you discovered general solutions, you can apply the boundary conditions. Boundary condition is the theta equal 1 and also d theta d g equals 0 at g equals 0. C sub 1 equals 0. C sub 2 equals 1. So solutions, theta is expressed 1 minus 1 over 6 g squares. So if you draw the thetas as a function of g, theta n equals 0 means a constant density starting from 1 and decreasing. And when the g equals square root 6, theta becomes 0. Okay, so this corresponds to the radius of a stars. I showed how to solve the Lane-Emden equations using the mathematics. We are going to derive some physical quantities. The first one is the total mass. Total mass is given by this equation. 4 pi r squared rho dr. 4 pi r squared d rho is a volume of the thin shell. Like a shell, we consider this is r. The width of the shell is expressed as dr. The volume of this shell is given by the 4 pi r squared is the surface of a sphere times the dr is a width. Give the volumes. So volume times density becomes a mass. So we integrate. So it becomes a total mass of a stars. You can change the equations using the g and the rho is use thetas. Then it becomes a g squares theta to the n. And the capital R is the radius of the stars is given by the alpha times the g sub 1. Then from this to the here, you can use the Lane-Emden equations. The equation is 1 over g squares d g squares d theta g equal minus theta to the n. So we pick up this and this becomes these equations. Then we could integrate over these quantities. It becomes the next line. The g sub 1 is correspond to the radius. You can write down the equations or use the radius of the stars r instead of the g sub 1. It becomes these equations. Average density is given by total mass divided the volume over stars 4 pi over 3 r cubed. So if you introduce the d sub n, you could write down the rho sub c equal d sub n rho var. This is a linear relation between the central and the average densities. So in the case of the n equals 0, d sub n equal 1 because it's uniform densities. In the case of n equal 5, actually d sub n is go to the infinities. So I showed some typical case of the n equal 1. Actually this equals the pi squared over 3. We'd like to move to the next topic of the relation between the mass and the radius. So from the first equation, this is a definition of the alpha squares. Then you can express the rho sub c with the alpha. Rho sub c is expressed alpha. And also from the last slide, I derived the total mass of the star is given by the minus 4 pi alpha cube rho sub c times g sub 1 squares d theta d g. So from these equations, m over minus g sub 1 squares d theta d g sub 1 equal 4 pi alpha cube rho sub c. For the rho sub c's, I have derived this expression. We can substitute these equations here, so it becomes 4 pi alpha cube 1 plus n k over 4 pi g alpha squares n over n minus 1. Then from these equations, m over minus g sub 1 squares d theta d g sub 1 n minus 1 equal 4 pi n minus 1. So you can change the alpha. It's r over g sub 1 3 n minus 1 1 plus n k over 4 pi g n and alpha changing g sub 1 over r 2n. So from this equation, you can keep changing the equation. M over minus g sub 1 squares d theta d g at g sub 1 n minus 1. Then r over g sub 1. This becomes 3 minus n equal 1 plus n k to the n over 4 pi g to the n. Use m sub n, r sub n. Then it becomes gm over m sub n, n minus 1, r over r sub n, 3 minus n, equal 1 plus n, k n, 4 pi g. So we derived this equation. This is exactly equal to this equation. We derived the relation between the mass, this is the mass, and the radius is related with this equation. Then from this equation, relation between the mass and the radius given by this equation. When the n equals 3, this term becomes 1. Mass becomes independent of radius. For a given k, there is only one possible value for the mass of a star that satisfies the hydrostatic equilibrium. In the case of the n equals 3, n equals 1. In this case, this term becomes 1. So in this case, the radius is independent of mass by looking at this equation. For the n equal between the 1 to the 3, r becomes a function of the distance. n minus 1 over 3 minus n is positive. So this becomes positive quantities. So this means radius decreases with the increasing mass. The more massive a star is, the star becomes smaller. So using the Lane-Emden equation, we discovered this relation between the mass and radius. Then also we'd like to find the relation between the pressures and densities. So from the last equations, Gm over Mn to the n minus 1 and then R over R sub n 3 minus n equal 1 plus n k to the n over 4 pi g. So from this equation you can express this k equal 1 over n plus 1 4 pi 1 over n g m 1 minus 1 over n over m sub n 1 minus 1 over n times r 3 over n minus 1 over r sub n 3 over n minus 1. So for this equation, you can substitute r. This r is from the density, central density is expressed d sub n over 4 pi over 3r cubed. So from this equation, r is gonna be 3 over 4 pi 1 over 3 1 over 3 m 1 over 3 rho sub c minus 1 over 3. You can substitute this capital R into the back to this equation. Is a polytropic equation. You can use k times rho sub c 1 plus 1 over n. So this k, obtained k, substitute back to this equation to find the central pressures. Then it becomes 4 pi 1 over 3 g m 2 over 3 rho sub c over 3 1 over n plus 1 3 1 over n minus 1 over 3 d sub n 1 over n minus 1 over 3 over m sub n 1 minus 1 over n r sub n 3 over n minus 1. We name it this is a b sub n. Then it becomes this equation. Substituting the k of the second equation into the first equation, we express the central pressures as a function of the mass of the stars and density of the central density of the stars times the b sub n. And by changing the n from the 1 to 3s, we'd like to calculate the b sub n. B sub n is a 0.23, 0.19, 0.16. Doesn't change a lot. So b sub n varies slowly with n. So relation between the p sub c and the rho sub c looks like independent of the number of the n. So p sub c is proportion to the rho sub c. The power index is 4 over 3. So we can use these equations independent of the n. This is the end of this session.